All right, welcome back. Today's lecture is going to be on decision errors in hypothesis testing. The goal of hypothesis testing is to make an inference about populations based on samples. Remember that when we state our research and our null hypotheses, we do so using population parameters. So for example, on average, our treated population will have scores that are lower than our population that does not get the treatment. Even though our hypotheses are about the relationship between populations, we test our hypotheses with a research sample. Furthermore, our conclusions are based on probabilities. Specifically, we say that we have a statistically significant result if the probability of observing our sample data is 5% or less based on a comparison distribution. Because our statistical decisions are based on probabilities, we need to consider that we could be wrong. So to help understand how we can make errors in our statistical inference, let's start with an example. So let's just say we work for a test preparation company and we have developed a new LSAT test preparation class. So the LSAT is the law school admissions test. This has historically and is still currently required by accredited schools in order to be admitted. And so there's many companies that are out there that try to help law school applicants get a better score on this test. Okay, so let's just say that we work for one of those companies. Well, we have 49 people that take our class, and we want to know, are their scores better than people that don't take our class? So we'll go through this example using our 5 steps of hypothesis testing. So our research and our null hypotheses would just be stated in terms of our populations, population 1 being people that have taken our LSAT class, and population 2, those that have not. Given our question, we want to know, are scores better if they take our class than those that don't? We'll state our research hypothesis as our class raises LSAT scores. That is, the mean of people that take our class will be higher on the test than the mean of people that don't take our class. And then the null hypothesis would just be that our class does not raise LSAT scores, which we would state in symbols as mu1 less than or equal to mu2. The second step would be to determine the characteristics of the comparison distribution. Now, we do actually know, and these are real numbers, that the average LSAT score is around 150. That is, mu is 150 with a standard deviation of 10, and that scores are normally distributed in the population. So our comparison distribution for these types of problems is a distribution of means. That distribution of means follows 3 rules. All right, now I'm just pointing out here that we need to recall that our sample size from the previous slide was 49 people. There's 49 people that do our test prep class. Okay, so a distribution of means follows these 3 rules. Rule 1 is that the mean of the distribution of means is equal to the mean of the population. So we can say that mu sub m is 150. By rule 2a, we can figure out the variance of the distribution of means. Notice that what I've done there is I've just squared 10 because the population standard deviation is 10. So our rule 2a, it's involving the population variance. So I just squared 10 to get a population variance. And then I'm dividing that by sample size. So we're able to determine that the variance of the distribution of means is 2.04. And then once we have the variance, we can just take the square root to get the standard deviation of the distribution of means. That is the standard error of the mean. And then by rule 3, the distribution of means is approximately normal, and we know that because we're sampling from a normally distributed population, and also because we have 49 people in our sample. So that actually satisfied both of those criteria for why we would have a normally shaped distribution of means. Okay, so applying those rules, we can say that our comparison distribution is a distribution of means. It's normal with a mean of 150 and a standard deviation of 1.43. Now, it's really useful to have this comparison distribution because we have a basis for comparison. What this distribution of means tells us are the possible values of sample means that could be sampled from a population with a mean of 150 and a standard deviation of 10 based on all possible random samples of size 49. So this essentially gives us the range of means that we could expect from any random sample of 49 people. And so what we can see is that obviously the thing that we would expect to happen most often is that if we sample from a population with a mean of 150, we expect that most of our sample means would be 150. But we can see that looking at -1 and +1 standard errors away, we can see that 148 is a pretty common value, 151 is a pretty common value. But then as we start getting further out in the distribution, a mean of 152, less common, a mean of 147, also less common. So this kind of tells us what we can expect based on a random sampling process. And so when we actually do our study, and we actually get the 49 people that are going to be in our class, we have a basis for comparing, is that a high or a low average that we got in our 49 people in our class. So at step 3, we're going to set a critical value. And so actually what we're interested in, based on our definition of statistical significance, are the means that happen 5% of the time or less in the untreated population. So we're going to be looking for a sample result that happens 5% of the time or less in this comparison distribution, which is kind of assuming that our class has no effect. So that's our definition of statistical significance. So when converted to a z-score, we're really looking for a result that happens 1.64 standard errors away from the mean. That is, would exceed a critical value of 1.64. Our fourth step is to determine our sample score on the comparison distribution. Okay, so here we actually have to say that we did the study. All right, so our 49 people that took our class, they scored an average of 153. I just made that number up as a for example. Okay, so our sample mean is 153. We're going to convert that to a z-score using our z-score formula, and doing so will give us a z-score associated with our sample mean of 153 of 2.1. So we can place that 2.1 in our comparison distribution, and because that 2.1 exceeds our critical value and it falls in our region of significance, we're going to reject the null hypothesis, and we're going to come to the conclusion that our LSAT test prep class worked at improving exam scores or LSAT scores on the average. Okay, so again though, that's our setup, and we want to return to the idea that in null hypothesis significance testing, we make decisions based on probabilities. So we sometimes make incorrect decisions. So even though our conclusion is that we reject the null, okay, in that example, and we conclude that there is a statistically significant effect of our class, what we have to tell ourselves is we could be wrong. Okay, so specifically, we concluded that our class was effective at improving test scores because the mean in our sample from people that took our class was unlikely to be randomly sampled from a population in which the mean is 150 and the standard deviation is 10. But unlikely does not mean impossible. What we literally determined is that our result is unlikely if we assume that the null hypothesis is true, That is, the test prep class does not improve scores. So our result is unlikely if we assume that our class didn't work. But strictly speaking, we could have obtained this result even if our class had no effect. Our result is unlikely to happen if our null hypothesis is true and our class has no effect, but it's not impossible. Because all our distribution of means is, all our comparison distribution of means is what would happen if we randomly sample from a population with mean 150 and standard deviation of 10, right? It's all possible samples of size 49. So what you can see is that our mean is still in that distribution. It literally could still happen. It would happen 5% of the time or less, but it could still happen. All right. So the definition of a decision error is an incorrect conclusion in hypothesis testing in relation to the real but unknown situation in the population. So for example, we decide that the null hypothesis is false when it's really true. Decision errors are possible because decisions about populations are made using samples and because everything is based on probabilities. So we reject the null hypothesis. We say that there is an effect if our sample mean is so extreme that it happens 5% or 1% of the time or less in the comparison distribution. Okay. It's all based on probabilities. Now we won't know when we've made, or you won't know when you've actually made a decision error, but we can know the probability of making each type of error. So the first type of error we can make is called a type 1 error. This is when you conclude the research study supports the research hypothesis, when in reality, the research hypothesis is false. Another way of saying this is that we reject the null hypothesis when the null hypothesis is actually true. Yet another way of saying this is that we say that there is a statistically significant result, but there really isn't. So in our example, we could have made a type 1 error by concluding that our class improved scores. We could have actually been wrong. We rejected the null hypothesis, and we could have been wrong in doing that. This could have been an error because the class might not have actually worked. We should tell ourselves that our result simply could have been due to randomness. Just good old-fashioned randomness, good old-fashioned random chance, or luck. In fact, anytime we reject the null hypothesis, we could either be correct, that is, our research hypothesis is true, and the null hypothesis is false, but we have to acknowledge we could also be incorrect. That is, the null hypothesis is actually true. There's no effect. There's no effect of our class, no effect of our treatment, no effect of our intervention. All right? And therefore, our research hypothesis is actually false. Alpha is the probability of a type 1 error. Alpha is the same as the significance level that we set, our conventional level of significance of either 0.05 or 0.01. So the lower our predetermined alpha, or probability, the lower the probability of making a type 1 error. So with an alpha set at 0.05, when we reject the null hypothesis, we're actually allowing up to a 5% chance that we got our results, even though the null hypothesis was actually true. The lower we set our alpha, the lower the probability of making a type 1 error. 0.05 is typically the highest alpha level that we set in the social sciences. We could also use that other conventional level of significance of 0.01, and that would be used to take even less risk of making a type 1 error. 0.001 is used to be even less risky. Now, a type 2 error, on the other hand, is when we say that the results are inconclusive when the research hypothesis is actually true. Another way of saying this is that we fail to reject the null hypothesis when, in fact, the null hypothesis is false. Yet another way of saying this is that we say we don't have a statistically significant result when, in fact, the research hypothesis is true. In our example, we actually could not have made a type 2 error. And this is because the only time that you make a type 1 error is when you fail to reject the null hypothesis. We didn't fail to reject the null, we rejected the null. Therefore, it wasn't even a possibility to make a type 2 error. However, anytime we fail to reject the null hypothesis, we could make a type 1 error. Okay? We don't definitely, or a type 2 error, sorry. We don't definitely make a type 2 error, but there's a chance we make a type 2 error. Because anytime we fail to reject the null hypothesis, you could either be correct, right? The null hypothesis is actually true, so failing to reject it is a good thing, and our research hypothesis is false, or you could be incorrect, that the research hypothesis is true and the null hypothesis is false. Beta is the probability of making a type 2 error. Researchers try to avoid this error by raising alpha, which lowers the critical value. When the critical value is less extreme, it's easier to reject the null hypothesis. So for example, at the 0.01 level, the critical value for a one-tailed test is 2.33. But at the 0.05 level, the critical value for a one-tailed test is 1.64. So it's easier to reject the null hypothesis at the 0.05 level when the critical value is only 1.64. And therefore, it's more difficult to make a type 2 error. So this graphic, also in the textbook, shows you the relationship between alpha level and critical values. Notice that at the 0.05 significance level up top, the critical values are lower than at the 0.01 significance level at the bottom. So this 2x2 grid, I think, is very useful to try to keep track the difference between a type 1 and a type 2 error. So your rows represent whether or not we actually reject or fail to reject the null hypothesis in our research study. This is what we actually do and we know actually happens. Looking at the columns, though, we've got whether the null hypothesis or the research hypothesis is true, which is something that we can't actually ever know. So the idea is that if we look at that top row, when we reject our null hypothesis and we say that we support our research hypothesis, we would be in error and make a type 1 error if in fact the null hypothesis is true, but we would make a correct decision if in reality our research hypothesis is true. Again, we can't ever know that, but we can just basically set up the probability of making one type of error versus another. If we go down to that second row, we would have a conclusion because we don't reject the null hypothesis, we fail to reject the null hypothesis, that our study is inconclusive. Now, if the null actually is true, and our class, our treatment, our intervention really doesn't work, it would be correct. It would be correct to conclude that. But if our research hypothesis is true, our class does have an effect, our intervention does have an effect, our training works, whatever it is, we'd be making a type 2 error in that case, saying that our results are inconclusive, but it really does work. Okay, so using the example from this lecture, if we, with our LSAT test prep class, it would be we rejected the null and conclude that our class improves scores. Well, that would be correct if our class does in fact improve scores, but it would be a type 1 error if our class doesn't improve scores. Okay. Alternatively, if we had failed to reject the null, we didn't in our example, but let's say we had, we would conclude that our class does not improve the LSAT scores. Well, That would be correct if it really didn't, like if it wasn't a good class, but we'd be making a type 2 error if we did have a good class, it did improve scores, but we just didn't have the statistical evidence to make that conclusion. So there's a relationship between type 1 errors and type 2 errors. If we lower our alpha to something very low, like a 0.001 significance level, we reduce the chances of making a type 1 error, but in doing so, we increase the chances of making a type 2 error. Alternatively, if we raise alpha to something like 0.10, we reduce the chances of making a type 2 error, but in doing so, increase the chances of making a type 1 error. So there's a relationship where if you raise the probability of making one, you lower the probability of making the other, and vice versa. Which error is worse? It really depends on the situation. So if it comes down to concluding that a defendant is guilty, we might be more concerned about a type 1 error, that is, concluding guilt when the defendant is innocent. You could think of something like a beyond a reasonable doubt standard that they have in the law as something that is very stringent, kind of like an alpha level of 0.01. Alternatively, sometimes the legal standard preponderance of the evidence is used. You could think of that as kind of less stringent, more like a higher alpha level like 0.1. In another example, we might think about having a life-saving drug or a life-saving vaccine. Here, we might be more concerned about making a type 2 error, concluding the vaccine doesn't work when it in fact does. Oops. Last point I'm going to make is that beta is not necessarily calculated as 1 minus alpha. We might be tempted to say, well, if alpha is the probability of making a type 1 error, I'll just do 1 minus alpha to kind of get the opposite, and that'll tell me what beta is. It turns out that 1 minus alpha is actually the probability of a correct decision if we are to assume that the null hypothesis is true. Beta, on the other hand, is the probability of an incorrect decision when the research hypothesis is true, which is not the same thing. Calculating beta requires calculating statistical power, which is a topic for the next time.